The goal was audacious.
That's radar face. We are seeing G's on the order of 11.
To find out if life could ever have existed on Mars.
Pressures have been reading. We're at 9 o'clock.
Signaled Odyssey is still strong.
And if the planet is safe enough now for human explorers.
Altitude of 8 kilometers. Valid range. Vigil has separated. We've acquired the ground with the radar. Standing by for batch separation.
Just getting to the surface was risky.
We are in powered flight. 500 meters in altitude. We found a nice flat place. Standing by for stack rate.
Requiring technologies never before tried.
Sky green is started.
Her journey was going to be complicated and dangerous.
Signaled Odyssey remains strong.
Tango Delta nominal.
All alone on Mars, the robotic rover would have to learn and adapt.
UHF is good. Touchdown confirmed. We're seeing on Mars.
And so would her human handlers. We are down. But where are we? There's the peak of Aeolus Mons, better known to the team as Mount Sharp. Our descent imaging camera is unexpectedly still working. We'll have an extra eye on the ground throughout the mission. And we are not alone. Mars Odyssey, Mars Express, and the Mars Reconnaissance Orbiter monitored the landing from orbit, relaying our telemetry through the Deep Space Network. Their timing was perfect. The high-rise camera aboard the reconnaissance orbiter captured us descending on parachute. The day here lasts 24 hours, 39 minutes, 35.24 seconds, nearly 40 minutes longer than an Earth day. It's called a sol. Above, high-rise has found us. The back shell, descent stage, our heat shield, even craters left by the tungsten ballast weights. We're about 10 kilometers from the base of Mount Sharp, our ultimate goal. It's the most accurate Mars landing yet achieved. We deploy our high-gain antenna. Now, we can talk directly to Earth. It's time to put up our mast. Curiosity had done this once before, in a test at the Jet Propulsion Lab. After the long journey, it now works on Mars. We take our first good look around. The team names this location Bradbury Landing, after the author of The Martian Chronicles. His 1950s collection of short stories told of the colonization of Mars by people fleeing an Earth ruined by nuclear war. a series of navcam images are assembled into our first selfie. Engineers had worried that dust kicked up by braking rockets would cover the rover. But Curiosity's decks appear mostly clear and ready for action. The team at JPL wipes more than 500,000 lines of entry, descent, and landing code, replacing it with surface mission instructions. Curiosity's onboard computers are a pair of radiation-hardened PowerPC chips bused to 2 gigabytes of flash memory and 256 megabytes of dynamic RAM. It takes the next 7 sols to upload and check the new software. Then, we are a spacecraft no longer, but a rover, eager to explore. Curiosity is a direct descendant of tiny Sojourner, the 1997 Mars Pathfinder rover, and a big brother to the rover's Spirit, now asleep on Mars, and Opportunity, still doing science about 7,000 kilometers away. Designed and built at NASA Caltech's Jet Propulsion Laboratory, every component of this rolling lab was tested, tweaked, retested, and refined. They sent power to the drive motors, performed a traditional shake and bake test, severe vibration, then heating and chilling in a vacuum chamber. They tested its ground-finding radar from an FA-18 Hornet jet and an AS-350 helicopter flying over terrain similar to Mars. They invented and perfected its supersonic parachute design. At the speed Curiosity would travel in the high Martian atmosphere, the chute would fill or fail in a fraction of a second. Test data would only have meaning if the team could see the failure modes. So these became the best photographed parachute inflations in history. They tried out their risky sky crane deployment
5,
with all of JPL watching.
2, 1, fire.
After long debate, the science team settled on a landing site, Gale Crater. At its center, Mount Sharp is built in layers, clays at the bottom, sulfur and oxygen-bearing minerals above, and complex channels carved long ago by flowing liquid at every altitude. The mountain offers a chance to voyage up through millions of years of geologic time on Mars. We've taken the frames of a complete panoramic picture now. Rocket blasts from our sky crane have scoured the surface in places which appear as light gray smudges. The geologists are fascinated by what the thrusters have uncovered. Curiosity's ChemCam finds its calibration marks mounted aft next to our onboard nuclear power source. By zapping bits of Mars with its infrared laser, Curiosity can tell what a rock is made of from up to 7 meters away. We target a fist-sized rock named Coronation, vaporizing a tiny area with a pulse hotter than the surface of the sun. We record the spectrum of the plasma ball from ultraviolet through infrared. The laser melts a spot less than 1 millimeter across. So we send a series of pulses to cover the mineral's variations. On Sol 20, ChemCam sends down its first raster of 5 side-by-side laser blasts. Our wheels print the letters JPL on Mars in Morse code to check if we're slipping on terrain. Rover drivers are eager to test Curiosity's navigation systems. Using visual odometry, the rover can drive short stretches all on its own. By Sol 26, we've driven over 100 meters, more than a football field length. Road test behind her, she's licensed to drive on Mars. Curiosity's reach for Mars began in the 3rd week of June 2011, when engineers bundled, bagged, and boxed the rover. Going from the high bay at JPL in California to the launch site at Kennedy Space Center in Florida took 36 hours, a specialized truck convoy, a C-17 military cargo jet, and some delicate moves with heavy equipment. In a clean room at Kennedy, each major component was final checked and reassembled. They had to finish on time. Earth and Mars only come together for transfer every 26 months.
5, 4, 3, 2, 1. Main engine start, 0, and liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
The program is in right on time.
Launch day,
And we have first pair and second pair. Everything is looking good.
November 26, 2011.
Pairing jet.
Curiosity separates cleanly from its booster.
We have spacecraft separation.
But that's just the beginning. Getting to Mars safely has proven very difficult. More than 58% of previous missions have failed to arrive. Cruising between worlds, Curiosity endures temperatures as high as 120 degrees Celsius and as low as minus 155 degrees Celsius. Flight engineers could make no more than 6 tiny course corrections to set up their perfect rendezvous with the red planet. The JPL team is into a rhythm now, and the tempo is Martian. Curiosity's handlers adjust their schedules to the longer Martian sols. They must start their work shifts about 40 minutes later each day. It's hard on human bodies and minds. It takes 5 weeks to come back into sync with Earth time, only to immediately drift apart again. Begun on the Pathfinder project, rover handlers have their own lingo for talking about time. Yestersol means yesterday on Mars. Tomorrow is Morrowsol, Nextersol, or Sol-Morrow. A day off is a soliday. Curiosity's sample acquisition system must work through a complex range of maneuvers. Her tool turret looks like a hunk of metal hanging on the end of a 2-meter arm. On Earth, it weighs 30 kilograms, but on Mars, it's only 11. Every move is meticulously planned, then programmed. Driving and drilling makes for a power-hungry rover. Spirit and Opportunity drew power from solar panels. But that poses challenges, especially during the shorter sols of Martian winter, and when dust settles onto the panels, dramatically cutting the power. So, for this rover, engineers chose a radioisotope thermoelectric generator, the RTG. It uses the heat of decaying radioactive plutonium-238 to produce 125 watts of electricity for at least 14 years. About 300 meters ahead, the cameras see a place where 3 different terrain types flow together. We call it Glen Elg. That's a palindrome, the same word read forward and backward, because we'll visit it on the way in and again on the way out. Long before Curiosity touched down, the geology team created a map based on orbiter images. They overlaid a grid. Each box, 1.5 kilometers on a side, is named for an Earth town of less than 100,000 inhabitants. When the team spots a noteworthy object, they name it after a geologic feature from its hometown on Earth. Curiosity's arm-mounted Mars Hand Lens Imager, or MALI, is much more than just a selfie stick. Like Sherlock Holmes, the rover carries this MALI magnifying glass to look closely at clues to past events. Curiosity can also examine herself. All is in order. MALI snaps its calibration target, including a 1909 Lincoln copper penny. The team now rotates the turret 90 degrees to calibrate the alpha particle X-ray spectrometer. If MALI is the rover's eye, then APXS is her nose. Between MALI and APXS is the sampling drill, with a brush-like dust removal tool, the DRT. Rounding out the tool turret is the complex Chimera. It can scoop soil, then sieve, sift, and send the sample into 2 labs located inside the rover. To do this, Curiosity executes an elaborate hip-hop dance of precision robotics. Watching Chimera pop and lock reminds us of Curiosity's actual size. None of her cameras can capture more than 2 megapixels. But by stitching images together, the rover teams get all the resolution they need. To precisely position Curiosity on a science target, rover drivers visualize various paths on a 3D terrain map, which can be lit for any time in the Martian day. On Sol 44, the APXS is tasked with making its first science sniff, and the Molly its first science close-up of a Mars rock. We name the rock Jake Matijevich to honor our friend and mentor who had passed away just after we landed. Every 6-wheeled Mars rover owes its basic design to Jake, the JPL mathematician turned engineer who was a driving force of the 1997 Sojourner rover. Through some clever improvising, the team gets APXS and Molly data of a spot already shot by ChemCam. We quickly determine that Jake's rock was born in an ancient volcano. This is Mars rover science at its best. Jake would have been proud. If you could stand next to Curiosity at mid-sol and shoot a panorama, the sky would look orange-yellow, just like this mosaic of raw images from the Mastcam's long lens. But human geologists grew up under Earth's lighting conditions. So, to make rock recognition easier, the imaging team processes many Mars images to approximate Earth colors. With the Martian sky now shaded blue, the landforms are much easier to recognize. And the American flag shows its true colors. It took a gutsy nation to commit more than $2 billion during the depths of economic recession to doing pure science on another planet. Perhaps citizens will someday read this plaque or gaze out over the fourth planet's remarkable topography with their own eyes. We have gathered enough data to make a bold announcement.
This is a rock that was formed in the presence of water.
Mars may not now be inhabited, but it definitely could have been. Our mission has found abundant evidence that water flowed here on ancient Mars and did so for a long time. It turns out Curiosity landed close to the end of an ancient river flowing out of Gale Crater's ring of hills. Rivers flowed down the slopes of Mount Sharp as well. As they hit flatter ground, these rivers splintered into many smaller streams, spreading out into an alluvial fan. Imagine yourself knee-deep in this brook on ancient Mars. As water flows past, you feel rocks and gravel tumbling and bumping along the bottom. This action wears off the sharp angles, producing the rounded pebbles Curiosity has been finding. This one is about the size of your thumb. All around us is the story of streaming waters, now long gone. A story borne out by previous rovers. Left behind, a cold desert, far drier than any place on Earth. Something terrible must have happened on Mars. We see a simple angular rock. The team names it Bathurst Inlet after a bay in Canada. Deploying Molly to check out what look like crystals, we find it's made of tiny grains, smaller than we can clearly resolve. A mystery unsolved for now. We roll into Rocknest, a wind ripple shaped by Martian breezes. It's a set of tiny dunes built up downstream of some stone cobbles. We'll spend the next 44 sols here. Curiosity begins by kicking the dirt like a batter at home plate. Known as a wheel scuff, this lets planners see the consistency of the material. She backs off to examine the results. We want to make sure the rover's scoop can work here. Rocknest is judged to be just great for digging. Curiosity places the Chimera over an undisturbed sand patch, grabs the sample, and shakes it. The scoop vibrates to level off the sample and to bring any big chunks up to the top. Mastcam can take video, though it doesn't do so very often because video is a downlink data hog. On Sol 62, a bright object on the dark ground makes the team hesitate. Have we lost a bolt or screw? Is some system about to fail? A close-up from Molly convinces the team the object is benign, probably just a bit of plastic from the landing. Scooping the soil at Rocknest shows a crust that is brighter and coarser than the darker sand below. Look close, and you'll see layers, like a mocha cake. It is not uniform. The sand has history. After a series of self-cleaning steps, we deposit a portion on the rover's observation tray, which the geologists call their playground. Chimera delivers a sifted sand sample to the Chemin instrument, our chemistry and mineralogy lab inside Curiosity's boxy body. Chemin fires a beam of X-rays the size of a human hair into the sand crystals. The angles at which the rays bounce off reveal which elements and minerals are present. This sand seems to have no organic molecules at all. It has sulfur, and it contains chlorine. Yes, the main element in bleach. More than 0.5% of every sample we take is made of the stuff used to launch and explode fireworks. These are perchlorate salts, caustic chemicals that cause thyroid gland problems in humans. Mars Phoenix, the first probe to land in a polar region, found similar salts in 2007. Perchlorates act like natural antifreeze. That may be why Phoenix detected liquid water on its landing legs, even though the temperature at that high latitude was far below freezing. Overhead, the Mars Reconnaissance Orbiter has been seeing hydrated perchlorate salts associated with features that look like water gullies running downslope. It's possible that Mars makes huge quantities of this stuff from nothing more than ordinary salt, silicate rocks, and the ultraviolet light that blasts through the thin atmosphere. Mars. Mars might someday become the propellant mining capital of the solar system. But having all this nasty stuff around will likely make colonizing Mars very challenging. It also turns out that about half the Martian soil around Gale Crater is composed of crystals of volcanic glasses, olivine, feldspar, pyroxenes, very similar to the weathered basalts on the flanks of the rugged volcanic Hawaiian Islands on Earth. Curiosity takes a selfie at the Rock Nest soil sampling site. You can clearly see our wheel scuff and our scoop marks. We can now confirm something else scientists have long suspected. Mars' atmosphere was much thicker in the past, and it held much more water than it does now. Sniffing the air, the SAM experiment notices the thin atmosphere has an unusually high concentration of heavy isotopes of hydrogen, argon, and carbon. This tells the tale. There was once a dense blanket of air around Mars, which was stripped away from the top. The MAVEN orbiter will later confirm that this loss is still happening. Earth's atmosphere is more than 100 times thicker than Mars. Why did the red planet lose its air? It may simply be a matter of gravity. Mars is only about a third the mass of Earth. Still, Mars does have wind and weather. The rover's environmental monitoring station keeps track of air pressure, humidity, temperature, and wind. On many sols at around local noontime, its barometer has recorded small dips in air pressure. These may be similar to the dust devils photographed by both Spirit and Opportunity. But there's no visible evidence of them here in the lowlands of Gale, where winds blow down from Mount Sharp in front of us, or from the crater's rim behind us. These winds are seasonal. Mars' orbit is much more eccentric or elliptical than that of Earth. That means the lengths of seasons vary much more here. Autumn in the southern hemisphere of Mars is the longest season. Spring is the shortest. Curiosity keeps track of seasons using an ancient instrument, a sundial. We take the largest photo yet. 3 different cameras contribute almost 900 images to make this 1.3 billion pixel panorama of Rock Nest, centered on Mount Sharp to the south. We can now visualize the ancient lake lying between where we are and where we're going. After 100 sols of pre-planned systems checks, Curiosity has gone from mechanical robot to field geochemist. As we set off from Rock Nest, Curiosity's drivers hand the keys to the science team. From now on, operations will be discovery-driven. The quest for domains of life will rule the mission. The rover is headed for Yellowknife Bay, a shallow depression with remnants of an ancient lake and stream beds. We're keeping our eye on a regional dust storm. It's far to our southwest, and we hope that it weakens before it arrives. We stop at Shaler Outcrop. Dramatic layering of the landscape excites the team. It was almost surely built by flowing liquid, pushing soil and sand like a migrating dune made of mud. Millions of years later, the rock layers are inclined. Where is all the water now? Curiosity can see water below the surface thanks to a neutron-shooting hydrogen-detecting instrument named Dan. Russian scientists contributed it to the mission. Since we left Bradbury Landing, Dan's data has been showing that the soil down to 60 centimeters depth contains as much as 4% water. Mastcam can also prospect for water. Looking at a rock named Nor, we find its signatures in pale veins and light-colored nodules. We've arrived at Yellowknife Bay. 3 different layers of terrain lie exposed here. It could have been the shoreline of a shallow lake. The lower plate rock is full of spherical bumps, technically called concretions, the calling cards of water that once percolated through mud. Does water flow anywhere on Mars today? The Mars Odyssey and Mars Reconnaissance orbiters have documented seasonal streaks running downhill. Seen mostly at latitudes around Mars' equator, the dark traces appear in late spring or early summer. Researchers call them active slope features. Based on the temperatures at those times, the most likely cause is salty water melting out of subsurface ice. The water, or whatever it is, doesn't flow constantly. And by late summer, the features fade. Curiosity will lose touch with Earth for the entire month of April 2013 as the Sun appears to slip between Earth and Mars, what's known as solar conjunction. So, JPL preloads the rover with 30 sols of autonomous science to do. One group of researchers thinks that a series of matted sheets in Yellowknife Bay look like structures produced on Earth by microbes over 3 billion years ago. Could some of these rocks on Mars have been made by microbes? Mars is now out from behind the Sun. We're eager to do more contact science. We choose another flat, veined rock less than 3 meters away from John Klein. The idea is to perfectly place the rover, her arm, and its turret. Then pick the exact drill location to maximize research and minimize risk. Cumberland is loaded with concretions that likely formed when water evaporated, dumping minerals behind. And so we drill our second 1.6 centimeter shaft into Mars. Then shoot a line of laser zaps to see what's in the tailings. Always learning from our rover, the team uploads new ChemCam code to make sure it never looks directly at the Sun, which could kill the instrument. We've come upon a mini cliff just 50 centimeters tall. It's full of holes, many of which have small islands of other material in them. Is it an igneous volcanic rock that bubbled? A sedimentary mud rock through which gas fizzed? Or liquid percolated? Another mystery. We've traveled 1 kilometer. 5 more ahead to begin climbing Mount Sharp. Some on Earth believe Mars could soon be a second home for humanity. But what the rovers are seeing looks like a ruined planet. Caustic dust and extreme cold challenge machinery, but could be deadly for biology. If you condensed all the water vapor in the Martian atmosphere, it would make an ocean only 1 millimeter deep. Curiosity's radiation detector started taking data as we left Earth orbit, sampling for 15 minutes out of every hour. How much and what kind of radiation would astronauts face? If you flew for 6 months to get to Mars, then explored the surface for 500 days, and took another 6 months to fly back to Earth, you'd absorb a greater than lifetime limit of radiation, with at least a 5% increased risk of fatal cancer. On Mars, there's little atmosphere and almost no protective magnetic field. You'd be hit by solar energetic particles, some of which come at you at 80% the speed of light. Supernovas, pulsars, and other highly energetic events far away blast galactic cosmic rays. Spacesuits offer no protection. To avoid damage to your DNA, you'd have to live underground. It's easier, safer, and much less expensive to explore Mars from Earth through telepresence. But real people can't live in the virtual world. Colonizing Mars will be very risky. Like watching starships passing in the night, if you sat next to Curiosity looking up through a small telescope, this is what you'd see. Curiosity catches Mars' inner moon Phobos sailing past its smaller outer brother Deimos in real time. Here's how big the Martian moons would look compared to Earth's. They're much smaller, but orbit much closer. On another sol, we stopped to observe Mars' tiny moons moving across the face of the sun. But neither is large enough to totally eclipse the sun. Curiosity sings herself happy birthday on the landing anniversary. No, not pre-recorded. The sample analysis apparatus vibrates to sift the scooped material. Sam's handlers at NASA Goddard Space Flight Center have programmed a sequence of shaker frequencies to play the famous melody. With Curiosity paused at Discovery Ridge, the software team uploads improved auto-nav code. She'll be able to cruise around more obstacles on longer drives by herself. On the long road to Mount Sharp, we pause at a location called Darwin. In one of the outcroppings, the rock cracked long ago. Fluid carrying minerals filled the crack, then evaporated. While the rock eroded away, the hardened minerals remained. The Mars Hand Lens Imager sends a high-resolution presidential portrait from Mars. At closest focus, each of Molly's pixels captures about 5/10,000ths of an inch. It's not the sharpest camera on Mars, but it's on the most mobile platform, allowing the rover to photograph a wide range of remarkable rocks. All around Darwin, the land is littered with rounded pebbles, another clue that water flowed through here. The layered terrain of Mount Sharp beckons. We're closer, but we need to get on the road again. ChemCam fires its 100,000th laser shot at a target named Ithaca. It turns up silicon, calcium, sodium, magnesium, potassium, aluminum, oxygen, chromium, manganese, and titanium, valuable building materials for future settlers, perhaps. Like much of the bedrock here, Ithaca was born in a volcano, ground into tiny pieces, and laid down as sediment at the bottom of an ancient waterway. We've driven almost 5 kilometers. Curiosity's 6 metal wheels are taking a beating. The hard, jagged surfaces lining the foothills of Mount Sharp have left punctures and dents in her metal tread bands. We adopt the strategy, drive less and drill more, to optimize the scientific harvest. We'll aim for a low sand dune we're calling Dingo Gap to give us a smoother road to the upper mountain. Overhead, Mars Reconnaissance Orbiter watches us make tracks. ChemCam's telescope snaps an image of Harrison Rock, then zaps it with the laser, revealing again distinctive signs of volcanism. This was a land of fire and water. We're rolling over the low dune at Dingo Gap now. It's just a meter tall, but if the sand turns out to be super soft, we could be in trouble. We go through it backwards. The first time we've done this. Looking back at our tracks, the dark color resembles mud. But don't be fooled. Mars is bone dry. Ultraviolet light, unfiltered by the thin atmosphere, bleaches the landscape. We've exposed the true color of the sand grains. We've reached a spot called the Kimberley. Up ahead, the full grandeur of the mountain. Looking down at the terrain, the team is starting to understand how this land was put together. Driving further only confirms the story. This was a river delta. We're working a sandstone fragment called Windjana, named for a gorge in northwest Australia. We brush away its rusty rind. We punch it with our hammer drill. It's the first rock we've bored into that isn't mudstone. ChemCam shoots the shaft. Its dark manganese dioxide would have needed strong oxidizing and lots of water to form. Windjana is telling us that winds of abundant oxygen blew through here in the ancient past. On Sol 640, the mast cam spies an iron meteorite lying partially exposed among the pebbles. The team names the meteorite Lebanon. It's probably a rare type known as a palisite, thought to form deep inside large asteroids. On a planet where life may have failed, we've discovered a shard of a world that shattered apart. Mars' thin atmosphere lets many such impactors through. Comparing before and after images from orbiters, more than 400 fresh craters have been discovered. Knowing the frequency and size of such impacts is important for understanding the dangers faced by future explorers. It's also critical for understanding the evolution of our solar system. Curiosity has now spent more than 1 Martian year, 687 Earth days, exploring Mars. She makes her own celebratory fireworks. The hand lens camera catches a ball of plasma, generated as ChemCam's laser hits a baseball-sized rock named Nova. We roll onto the sandy floor of Hidden Valley. There's a clutch of bright, flat stones rising amid the sand, and a promising target, Bonanza King. We brush and drill, but it's too wobbly and the sand too slippery. We choose a better route, with better rocks, and rove on. Back on Earth, some tiny microbes are threatening to change the way science is done on Mars. A study has revealed that certain microorganisms can survive the cleanroom sterilization techniques used on spacecraft. Some may have hitched a ride to Mars with us. Curiosity isn't capable of seeing microbes directly, either native Martians or transplants from Earth. We'll have to be extra careful in evaluating any organic material we pick up. We come upon what looks like a mammal thigh bone. It's just a weathered rock, of course. Mars probably never had enough oxygen to support life larger than microbes. Curiosity has come nearly 7 kilometers. It's time to climb. At a stop on the lower slope, the onboard labs find a sharp signature of hematite. Working mostly in the stable temperatures of Martian night, the SAM finds these rocks have undergone much more oxidation than others. Just what happens when wet rocks are repeatedly exposed to dry atmosphere. Next stop, whale rock. Here, ripples of water slowed down as they slipped into an ancient lake. Flowing across the bottom and dropping their mud and stones to make the layers of the whale and other nearby rocks. This is exactly what happens on Earth, where rivers fan out into bodies of open water. The science team has reached consensus. A series of large lakes once covered much of the floor of Gale Crater. Layers of silt built up over tens of millions of years. The stacked strata tell a tale of recurring lakes, winds, river deposits, and dry spells. Of a climate in cyclical turmoil. The 5-kilometer-tall mountain grew very slowly. The evidence here shows Mars' lakes, and perhaps its oceans, grew and shrank and grew again for millions of years. Did a moist Mars long ago nurture life? We've climbed up a bank, leaving us parked at an 18-degree tilt. This is the steepest angle we've tried to work. Some drivers are concerned that it's not safe. But everything about this mission has been bold. The team goes for the science. Curiosity brushes the rock named Santa Ana. Our science nomad machine stays rock-solid stable. Holiday time on Earth again. 10 sols of science assignments are beamed to Mars. NASA and Microsoft announce a unique joint venture to put scientists on Mars. Human geologists would like to walk sites like Gale Crater, to see rocks up close, survey the terrain, confer with one another, and ponder Mars history. So a new system called OnSite is designed to let scientists interact on the Martian landscape in virtual reality. It could set the stage for how humans and robots will interact in the future. We get on the road out of Pahrump. There are weird rocks with bright veins up ahead along a pass called Artist's Drive. One wonderfully complex feature calls out to the science team. It looks almost like a fossilized skeleton. We name it Garden City. The surrounding rock has eroded faster than the veins, leaving lighter walls standing, about as high as a kitchen carving knife is wide. Such streaks are laid down in lakes, streams, shallow seas, and hot springs where the water has evaporated, leaving deposits to concentrate and crystallize. Here, Curiosity measures many different minerals intersecting and cutting across each other, including calcium sulfate and magnesium sulfate, each one spiced with traces of elements like iron and fluorine. This strongly points to many episodes of waters washing through from far-off lands, each time leaving their distinct chemical calling card, hinting at where it came from. On Earth, eroded hillsides marked by similar veins are common in places where water comes and goes over the centuries. That's just what Curiosity is seeing along Artist's Drive on Mars. A fossil record of many wet and dry times long ago. The Mars Reconnaissance Orbiter sees us rolling through the pass. More than just tracking the rover, MRO has kept watch as the winds of Mars try to bury all evidence of our landing. The blast scars from our descent stage are healing. Heat shield marks sinking under sand. Our back shell getting buried. The remains of our parachute flapping in the thin Martian wind. Curiosity alone escaped the shifting sands by rolling away. Red and yellow dust lets mostly blue sunlight through, so the Martian sun always appears bluish. We see this effect clearly at sunset when light travels a longer path through a larger slice of atmosphere. Before the blue sunset tomorrow, we will have rolled 10 kilometers. The valley here is lined with sand. We're seeing thicker and more frequent wind ripples. and the terrain between them is steeper than we've encountered before. We'll have to choose between risks: getting stuck in sand or slipping off barren hillsides. Our Lincoln penny may be getting dusty, but it's none the worse for exposure to the thin, cold air, ultraviolet light, and cosmic radiation. We decide that climbing the hills is safer than risking the sands. Curiosity has proven herself a sure-footed mountain goat. So up we go. And the effort pays another dividend. We're at the transition between two major layers of bedrock. Darker stacks of Stimson stone overlie pale mudstone of the Pahrump Formation. We park the rover up here in the rough country and put the instruments in resting mode. Solar conjunction is coming, and we'll soon have the sun between us. The DAN instrument reports the greatest concentration so far of subsurface hydrogen, a proxy for water, almost 7 times higher than at any previous site. It will fall to a future rover to drill at meter-scale depths. We brake to snap images for a low-angle selfie. Of course, we're just a machine, but NASA knows that these self-portraits are a key to keeping the public actively engaged. Each selfie is rehearsed by Curiosity's clone back at JPL. The Stimson formations offer what seems at first a treacherous route. But blowing wind and flowing water have smoothed natural paths through these forbidding lands. This particular pathway is one that connects Mars with its sister planet, Earth. It's as if a piece of the American desert Southwest has been transported here. The Stimson rocks are sand dunes frozen in time. The inclined layers display what geologists call cross-bedding. But it was wind and not water that sculpted them. A human field geologist would identify a rock, crack it open, extract a sample, and bag it for later chemical analysis, all in about an hour. Curiosity often takes 5 or 6 sols to do the same work. But all the while, the rover is multitasking. She's doing geochemistry, surveying distant terrain, and grabbing yet another self-portrait, like this one, at a location called Big Sky. Though Mars is now over 20 minutes away at the speed of light, our comm system of radios, orbiters, and big dishes allows engineers to closely monitor the rover. Our wheels aren't worrying us anymore. Long before landing, MRO images showed large fields of dark sand dunes between our landing ellipse and the higher elevations of Mount Sharp. From down on the ground, the dune wall looks imposing. The team names the first one Ralph Bagnold, after the British Army engineer who first studied the formation of desert dunes on Earth. Is different from a wind-blown ripple of sand. While the side facing the wind is gently angled, the downward side of a dune is steep and prone to collapse. That allows the dunes to roll across the land like waves on the sea. But dunes on Mars are very different from those on Earth. In the lower gravity and lower air pressure, they grow huge swirling ripple features. They creep across the landscape at about 1 meter each year. The dark dune here, named Namib, rises 5 meters at a 28-degree slope, a potentially formidable obstacle. Early on, JPL had verified what Curiosity could handle. Scarecrow is a test rover that weighs on Earth what Curiosity weighs on Mars. The team had taken Scarecrow out into the Mojave Desert to test drive on dunes of similar slopes and textures to those at Gale Crater. The decision is made to drive along the dune line on solid ground. So the team interrogates orbiter images to find a route around them. Exposed bedrock opens the way to a wind-blown sand field. It's the horn of the dune. The sand grains here are about as small as finely ground coffee. Curiosity tiptoes a wheel into the sand, making a test scuff, then gets down to serious science. After a month in the sand, Curiosity sets off onto the bedrock once more. She's now put 12 kilometers under the wheels, and all systems are still go. We named this stretch of sandstone bedrock after Bruce C. Murray, a former director of JPL. Murray saved the U.S. Planetary Science program when its budget was under heavy fire. He co-founded the Planetary Society. Bruce passed away in August 2013. he would have loved this place. As we make our way up Mount Sharp, we notice the rocks are more silicate, not like the volcanic basalts of our landing site. It turns out that most of these higher lands are made of tridymite, a rare mineral on Earth. We don't yet know why there's so much here. More Mars mysteries for future missions to solve. We've made it to the Naukluft Plateau. Now, we can see our way around the Sea of Dunes. Up here, the stacked stone of the Stimson Formation overlays the Murray bedrock. It's been sculpted by wind-blown sand. We're seeing nodules, much like the so-called blueberries discovered by the Opportunity rover in 2004. Were these little spheres made by water percolating through rocks? Were they the product of volcanoes? Or infalling meteorites? No one knows for sure. From here, we can look out to the peaks of Mount Sharp. And the raised rim of Gale Crater. You get a good feel for the terrain watching this simulation of Curie crossing the Naukluft Plateau. Her motion here is highly sped up. She usually roves no faster than about 1 meter per minute. But her route is correctly mapped onto a mosaic of mastcam images supplemented with high-rise data. And she's the only thing moving on the lonely landscape. More stops along the way, including broken ground we informally called Fracture Town. We'd seen it from orbit. It's nice to be here at last. Curiosity is getting more data from each location now. She is a physical extension of the scientists and drivers on Earth. portrait of the rover as a 2-year-old. She's reached 2 full years on Mars. That's nearly 4 Earth years of rolling science on a very alien planet. Curiosity is picking more of her own targets now and starting to do science by herself as soon as she rolls up to them. Imagine, someday, taking a walking tour of Curiosity's voyage yourself. Martian winds will have erased many of her tread tracks. So you navigate drill hole to drill hole. That Curiosity came this way all those years ago. And left these subtle science marks in Mars. The going is rough, but it brings us to a remarkable place that resembles coastline on a windswept ancient sea. Fitting, as we're in the Bar Harbor main quad on our map. And here's Egg Rock, a nod to the residents of Egg Rock Island off the Maine coast, and perhaps the strangest rock we've seen on Mars. It's a nickel-iron meteorite, no bigger than a golf ball. It may have landed here millions of years ago, but it appears incredibly smooth and fresh. Curie is telling us that our drill bit didn't extend to touch the surface as it should have, so she shut down the drill sequence. We've successfully bored into rocks at 15 locations using our hammer action punch before drilling method. But once in a while, the percussion mechanism has short-circuited. We'll now switch to drilling only, no tapping first, where the terrain is soft enough. We had intended to try that here at Precipice Rock. But we'll wait until we fully understand the issue by running tests with Curie's clone here on Earth. We've climbed 165 meters in altitude from our touchdown back at Bradbury Landing, most of it since leaving the Murray Buttes. The farther uphill we travel, the younger the landscape becomes. We're finding more clay minerals up here. There's now more hematite than magnetite in the rusty rocks. That may mean the environment was warmer when this land was formed. Small amounts of boron in the veins suggest, perhaps, an evaporated lake further up the mountain. This was a chemical reactor long ago, the sort of mixing bowl from which early life on Earth derived its energy. We've shifted strategy from drilling only where we see new terrain to sampling more regularly, about every 25 meters elevation, so we can build an accurate history of how the mound of Mount Sharp rose. We're being cautious with our drill, but overall, Curiosity is in remarkably great shape. Our rover drivers have long since learned how to minimize wear to the wheels. Our science instruments are tuned up and singing. The RTG power source is strong. New curiosities are turning up among the rocks. But the road ahead is uncharted. One mistake could bring this grand voyage to an end. Curiosity's legacy is already set. It's the finding that if Mars ever hosted life, it could have flourished here, amidst the lakes, rivers, and streams, whose traces we see etched in the ancient landscape. So we'll keep climbing, keep piecing together the story of water as we listen for the narrative of life echoing in the rocks of Mount Sharp. We'll continue on, ever curious.